Welcome, everyone, and thanks for joining another Silicon Labs product podcast. As I mentioned in our last episode, we're joined again by Mark Hallam. He's a field applications engineer here at Silicon Labs. And on our last podcast, Mark and I opened the topic about OpenThread, and there are some more technical questions that I thought Mark would be the best person to answer. Mark, you ready to go?
Yeah, let's do it.
All right. The first one is, what is the number one thing that you find yourself providing engineers who are, needing technical support for Thread? Where do you see them really asking you for support, and where are their designs stalling out?
Sure. So I referenced a couple of these things in the last podcast, but the first place that I'd recommend going is, of course, to the openthread.io page. That also has a link, like I said, to the GitHub repository, github.com/openthread. Those are really good references for the stack itself. Of course, if you want to know more about our hardware, we have our SDK and our own manuals and so on. However, those are the first places I would go. I also mentioned threadgroup.org to obtain a copy of the thread specification so that you can understand the stack itself. You'll find that there are a number of white papers that the thread group also has on that page in order to give you an understanding of the fundamentals of Thread and how it works, a lot of diagrams and things like that to help you understand the protocol at a fundamental level. I would say the other thing that I want to mention is that Silicon Labs will be very soon introducing their own SDK being deployed with Simplicity Studio. That will have OpenThread running as its basis, and then having a number of applications that we have already reporting to OpenThread, and of course all of our tools and things that are available there. We'll also have application notes and things like that to support this as well. But for now, for people who are trying to get up and running with OpenThread, those are the first two places to go, is of course to the GitHub and then to the OpenThread site, because it's going to have the most documentation specifically on that stack. Moreover, I mean, obviously, I've been doing this for a little while now, supporting Thread and OpenThread. So, especially if this is for somebody internal to Silicon Labs, I'd also recommend just reaching out to me directly. I answer a lot of these questions on a regular basis, and I can certainly help direct people in the meantime until we have our full SDK release at the end of December, at which point we'll have our own applications teams up to speed, and they'll be able to answer questions relating to OpenThread and implementation on EFR. So with regard to that, we're partly in limbo right now, just waiting to get our full solution deployed, but as soon as we have the full deployment, we'll be able to answer questions through our regular support portal, and we'll have engineers waiting to do just that.
All right, and I know it's still in development, and you just mentioned that, but so there is an offering right now in the GitHub that shows Silicon Labs support for OpenThread, but you mentioned the SDK release in December. Can you kind of quickly what's the difference between having it in the SDK and having it on GitHub?
Yeah, sure. So a couple of things. First of all, in the GitHub today, and I'll elaborate a little bit more, if you go down into the GitHub examples repository, you'll see examples for the EFR32 MG12, which is one of our Series 1 devices. And then we have an example in there also for the EFR32 MG21, which is the first of our Series 2 parts. So those examples fundamentally just bring up an OpenThread network, and you can transmit messages and ping out to the greater internet. So there's enough functionality there to be able to get up and running and build out a Thread network. There's also the ability to set it up as a network coprocessor so that you're able to connect it to really any Linux-based host and deploy, a network that, like I said, can also ping out to the internet. Now, in terms of our SDK, the difference there is that our SDK will also contain application notes. It'll contain a number of software examples that also integrate some level of application layer connectability, and also some fundamental functions like testing temperature or things like that. So we've historically had our own thread stack, and we're going to be porting a lot of the examples that we had there. So in terms of getting more, light to switch type functionality or sensor actuator functionality, things that we've had historically, we're going to be porting those things to Open Thread, and so we'll have more functionality on that side as well. The other thing that our SDK includes is our own schematics and things like that for our boards. So you'll be able to get a lot more information about how to properly integrate Open Thread specifically with Silicon Labs parts than you would be able to get in the GitHub itself. And of course, that's all contained in our own tool suite, which also has tools that allow you to read packets that are being transmitted through the network and decrypt those so that you can do better network debugging as well.
Okay, and you touched on the devices that currently support Thread. That's the EFR32 is our wireless MCU, and then you mentioned it's the EFR. Well, why don't you just tell the audience which ones are the devices that support Thread?
Sure. So yeah, I think I do think that's really important to cover. So right now we have support for the EFR32 MG12 and the EFR32 MG21. Now, we do have other devices in our portfolio, for instance, the MG1 and also the MG13. Right now, as of this point in time, we don't have support for those devices. There is some plan to bring support to that MG13, but right now it's for these two devices that have 1 megabyte of flash. And part of the reason for that, I think, answers another question that was also in regards to the limitations. So one of the main limitations in Thread, or really in any one of these protocols that handles mesh networking, is RAM limitations. So our other devices, the MG13 and the MG1, both of those have a lot less RAM than the MG12 and the 21, which have 256 kilobytes and 96 kilobytes of RAM respectively. One thing to consider whenever you're designing devices that are line-powered routing devices in a Thread network is that per child device in the network, you typically have to have at least 120 bytes of RAM available. Now, if you look at the Thread specification, per parent device, you're able to have up to 511 children per parent. So whenever you do the math on that, you start to see that that can actually take up quite a bit of RAM if you want to support the full functionality of a Thread network and have all of the children connected to the parent that you could possibly have. Now, to elaborate on that a little more, I would say that most of the ecosystems that are developed today, and probably most of them for the future, will limit that to 32 to 64 devices per parent. But I think it's good to be cognizant of the fact that if you want to have full support, you need to have a pretty robust MCU with 512 devices in the network.
So the theoretical maximum or the largest network would be 512. But like you say, for performance and just for cost and device support, sometimes they restrict it to under 60 or 50.
Yeah, I might clarify by saying that that's the number of children that each parent device can have in the network. That's not necessarily the maximum number of devices that can be sustained in the Thread network. However, the 32 to 64 number that I pointed out, in the case of, for instance, Google's network, they limit it to 32 to 64 children per parent device. So that means that if you want to add another routing device in the network, like another light bulb or some other device that fundamentally can relay these packets, that device could then add support for another 32 to 64 devices and so on. So there's more flexibility there, but per parent device, you're limited to 511 children.
Okay. So another one is what are the design decisions, we talked about the network size, but what are some other design decisions that can impact the performance of Thread? I've heard, latency, power, the range of the network. What are some of the design decisions that people are making that impact that?
Right. Yeah. So One thing I'll mention is that it's very similar to Zigbee in this case, due to the fact that they're both fundamentally based on the 802.15.4 standard. However, yeah, there are quite a few things that you have to take into account. I mentioned the application layer, and you already brought this up a moment ago. Your application layer can heavily impact the network. So if you have a particularly heavy application layer which requires packet sizes that exceed the standard packet size for the Thread network, you may end up finding that it requires a lot of packet segmentation, and then of course your devices have to relay multiple segments of the packets, rebuild them, and then see what was in that packet and respond to it. So in regards to your latency, that's going to be heavily dependent on your application layer. Fundamentally, Thread has one of the lowest latencies of any mesh networking protocol. However, like I said, when you select an application layer that might be a little bit heavy, that's going to impact your latency drastically. Another thing that you mentioned already is power consumption. So, of course, a lot of people out there and the reason that a lot of these protocols were designed, these mesh networking protocols were designed, is to allow battery-powered end devices to communicate with small packet sizes over short range with low latency. And the idea fundamentally here is to have a robust network that can then relay those packets rather than having to have a direct point-to-point connection, which can obviously take up a lot of power. So today, one of the things that you have to consider is the types of devices that you're expecting to connect to. A lot of manufacturers solve this problem by really designing both ends of the link. So they may design the gateway device, they may design routing devices, and they have their own sensors. So that's very common, for instance, with security vendors. So a security vendor might have smoke detectors and sensors and things like that. But they might also sell, for instance, thermostats or other devices that could be line powered and stay on. So it's really important to understand the network that you're planning to connect to, because that has a major impact on battery life. We're starting to see a lot of manufacturers who come to market with a number of sensors that they want to connect to a gateway, but they don't consider the fact that they don't have any routing devices in between, and eventually they're really just creating a point-to-point network that requires them to increase the output power and then drain the batteries on their devices. So it's really important to consider what you're connecting to at that point. And I think that also factors into range as well. But the other thing I'll take into consideration is coexistence. So when I refer to that, I'm really referring to the idea that you have a number of wireless networks around that are fundamentally operating in the same band, usually in this 2.4 gigahertz range. And especially if that's Wi-Fi, for instance, which sits on one channel and doesn't move to other channels typically, you could have a lot of devices that are transmitting at the same time, and that effectively raises the noise floor to the point where the receiver has to be able to hear the packet, and that of course means that your device has to be transmitting at a much higher power as well. That isn't always feasible. If you have Wi-Fi transmitting and co-located with a device or a radio that might be operating in the same band like this Thread radio, it can essentially just clobber all of those packets so they can't be heard. So it's really important to understand what type of device you're creating. Are you creating a gateway? At which point we need to start talking about how we're going to manage Wi-Fi trying to transmit and stream while that 15.4 network needs to be able to get its packets to that device. Are you designing a light, which just might be in a place that, like a commercial building that has a lot of Wi-Fi networks or Bluetooth devices and things like that? Are you designing an end device that might not be very close to the routing device, at which point it needs to increase its output power, like I mentioned, so that it can be heard over other radios that are nearby? There are a lot of factors that come into play here, and it can certainly impact all of the things we mentioned: latency and, of course, the power consumption of your devices if they have to completely retry all of their transmissions to be heard. That has a really big impact on the battery life. So I think those are just a few things to consider.
All right. Well, that's a lot of good considerations for the customers and for our audience to just be aware of. I like the coexistence information. That was very helpful. Thanks, Mark. Is there anything else you want to mention before we end this podcast for the listeners?
I would say for now, as I mentioned, Silicon Labs is working on deploying our own SDK, and very soon we're going to have the ability to support you on these types of device designs. Just wait, and you'll see some good content coming out very shortly.
All right. Well, thanks, Mark. Your answers, they've really helped me better understand Thread. I haven't looked into it for a while, so that was very helpful, and I'm sure our listeners benefited also. So for everyone that listened to this podcast, we appreciate your time, and stay tuned for other episodes coming soon.